Welcome to today's Explainer. If you're putting together notes for something like the UPSC GS3 paper on science and technology, where you're just fascinated by the bleeding edge of human knowledge, this is exactly the kind of topic you need to wrap your head around. Today, we're unpacking the colossal stakes at CERN. We're looking at a machine that literally recreates the conditions fractions of a second after the Big Bang, the multi-billion-dollar effort to upgrade it, and, well, the pretty fierce scientific debate over what comes next. Let's dive right in.
To really appreciate what we're talking about today, we've got to start with this wild concept of energy density. So picture a flying mosquito. The kinetic energy of that bug is trivial, right? But imagine taking that exact same amount of energy and cramming it into a speck that is 1 trillion times smaller than the mosquito. That staggering density is what 1 tera-electron-volt, or TeV, represents. And inside the collider, a single collision briefly creates the fiery furnace of the newborn universe.
But here's the crazy part. To achieve that microscopic, universe-birthing collision, you need machines on an absolutely incomprehensible scale. Hundreds of meters beneath the Franco-Swiss border sits the tunnel of the Large Hadron Collider, or the LHC. Above ground, it's just, dull gray buildings. But down below, it is a hive of colossal engineering unlike literally anything else on Earth. Okay, so here's our roadmap for this explainer. We'll start with the giant particle smasher. Then look at the triumphs of the LHC, followed by solving physics' biggest mysteries. After that, we'll cover the high luminosity upgrade. And finally, we'll tackle the $19 billion question.
Starting with Section 1, the giant particle smasher.
So how does this beast actually work? The LHC is essentially a massive 27-kilometer ring. Inside this ring, physicists take protons, the particles sitting right at the heart of every atom, and they drive them to just a tiny sliver below the speed of light. Then, they smash them together. Using massive detectors, like ALICE, scientists basically sit glued to their monitors, watching the multicolored swarms of particles left behind by each collision. They are literally sifting through the debris to find clues about how the universe was built.
But before we look at what they've actually found, we need to understand what they're testing in the first place, which is the Standard Model. This is the theoretical framework that has successfully described the whole architecture of fine particle physics. It explains that ordinary matter is built from quarks, those elementary grains that bunch together inside protons and neutrons, all held together by a strong force. The whole point is, the LHC was built to test this Standard Model. So, did it work?
That brings us to Section 2, Triumphs of the LHC.
And the answer is a resounding yes. Since its very first collisions back in 2009, the LHC has delivered some spectacular confirmations of what the Standard Model predicted. The absolute pinnacle was discovering the Higgs Boson in 2012. That's the elusive particle that actually gives elementary particles their mass. But beyond that, it's verified the existence of about 80 new hadrons, which are composite particles of quarks. It even briefly created quark gluon plasma. That's a searing hot soup of unbound particles that filled the universe in its absolute first microseconds. It's incredible stuff. But, science is never truly finished. While the LHC confirmed the Standard Model brilliantly, it also highlighted exactly where that model hits a brick wall.
Moving on to Section 3, Solving Physics' Biggest Mysteries. Because as incredibly successful as the Standard Model is, physicists are desperately searching for what it cannot explain. And we're not talking about small gaps here. The current framework gives us zero explanation for the existence of dark matter, or dark energy for that matter. Plus, recent LHC experiments have looked into the fundamental imbalance between matter and antimatter in our universe. But that mirror twin antimatter has proven just incredibly elusive. These signs of new physics have stubbornly failed to show up. So what do you do when your 27-kilometer, multi-billion-dollar machine isn't finding the answers? Well, you upgrade it.
Section 4, the high luminosity upgrade.
$1.5 billion. That is a massive operational pivot happening right now. The control center at CERN is actually going quiet as the LHC's beams are turned off ahead of what they call its third long shutdown. Over the next 4 years, and at this immense expense of roughly $1.5 billion, the entire collider is getting a massive overhaul.
So let's break down exactly what this high luminosity upgrade actually entails. First, like we mentioned, is the 4-year shutdown. Second, when it finally powers back up, the machine will be upgraded to energize protons step by step up to 6.8 tera-electron volts per beam. But the real magic? That's step 3. The proton beams will zip around and collide 5 times more often. This is literally giving scientists way more bang for their buck. By bumping up the collision frequency, they've vastly increased the odds of finally spotting those exotic particles and elusive signals they need to break past the standard model. But here's the catch. The LHC cannot run forever. Actually, scratch that. It has a very strict expiration date.
Which leads us to Section 5, the $19 billion question.
Because these machines take literally decades to plan and build, a successor has to be conceived right now, or it won't happen at all. Just look at this timeline. We had our first collisions back in 2009 and the Higgs Boson discovery in 2012. And we know the current LHC runs out of steam around 2041. So looking ahead, in May 2026, the Cern Council has to make a massive, point-of-no-return build or abandon decision on what's called the Future Circular Collider, or FCC. If they approve it, construction starts around 2028, with a potential 100 TeV proton machine following way later in the 2070s.
And guys, we are talking about a sheer jump in scale here. Compare our current machine, a 27-kilometer ring getting a $1.5 billion upgrade, to the proposed FCC. The FCC would be a staggering 91-kilometer-long tunnel with a breathtaking cost estimate of nearly $19 billion. And interestingly, in its first phase, the FCC would actually smash particles at lower energies than the LHC does today. Sounds counterintuitive, right? But it's because it'll be built for absolute precision, to pin down measurements perfectly, rather than just brute raw power.
As you can imagine, the debate over whether to spend $19 billion on this new machine is incredibly fierce. To look at this objectively, we have to weigh both sides. The driving argument for building it comes down to a sheer scientific necessity for more information. Take Dr. Archana Sharma, a Cern physicist, who notes, "We were very lucky with the Higgs boson. We need more data, and this is exactly why we are upgrading the LHC." The general consensus among physicists pushing for this massive project is that it's absolutely vital to push the boundaries of particle physics. And that means investing heavily at the design stage today, so we don't miss the boat entirely tomorrow.
On the flip side, though, there is some major skepticism about the real value of that massive investment. Not everyone in the scientific community is convinced that precision alone justifies the towering price tag. Physicist Sabine Hossenfelder has argued that such a machine, especially in its initial lower energy phase, would mostly just pin down quantities we already know, merely calculating them to a few more decimal places. And honestly, in an age of global conflicts and really frayed national budgets, asking governments to fund a $19 billion tunnel just for fractional precision, that is a deeply difficult proposition to sell.
Which brings us to the ultimate question that Cern, and indeed the entire global scientific community, is facing right now. As the LHC powers down for its $1.5 billion tune-up, the focus isn't just on the incredible things it has already found, but on the future. Is something even bigger, at a staggering cost of $19 billion, truly worth building? Does the quest to understand the fundamental, microscopic fabric of our universe justify that astronomical financial cost? Or are there limits to how far and how deep humanity can really afford to dig? It's a huge question to ponder. Thank you so much for joining me for this explainer. Keep focused and keep learning.